Good afternoon, everybody. I'm D. Mitra, talking to you from Marine and the Atmospheric Science Department at IRS at Dehradun. Today, my topic is basically remote sensing for coastal hazards. How remote sensing can help to address the various kinds of coastal hazards that we'll see, and what is the main use of remote sensing and GIS to address those issues. If you see that our space program, that we can divide into two ways. One is your communication and one is the remote sensing. Communication is basically the use the inset series of satellite data. They will be using for the radio, TV, DTH broadcasting, disaster warning, search and rescue system. This is one side. Basically, they are all we call them geostationary satellites. But which is of our interest for today's lecture is the remote sensing satellite or Indian remote sensing series of satellite like IRS-1A, 1B, 1C, 1D, ResourceSat, Ocean Color Monitor, those kinds of satellites. They are mainly used for the national natural resource management and mapping, hazard and risk assessment, relief, then various kinds of drainage assessment and their rehabilitation. They are the major use for the remote sensing satellite, and that is the talk of today basically. We are not going to cover anything pertaining to the inset series of satellites. First, the most important is that why satellite survey is required to address the hazard or disasters. If you see that satellite data is the only means to getting accurate, reliable and quick information due to the synoptic view, that means huge area you can see in a single scene, multi-temporal coverage, that means same area you can see in a different time domain, from various space-bound sensors with different capabilities. That means in the same area that can be observed from optical data, that can be observed from the active sensor or the microwave data, that can be observed that other kind of data, or you can go for the aerial platform also, the same area. So you can get various sources of information of the same area from the different kind of sensor, whether it is space-bound or it is airborne. And they may be of the different even spectral resolution, different kinds of spatial resolution. That is one of the most important part of satellite survey. And another most important thing, that whenever any disaster happens, the first thing which goes is the communication link, and you cannot reach to the place because all your road networks, rail networks and those things used to get devastated. But at least to get the idea about the area, like if there is a flooding, how much area has been flooded, if there is an earthquake, how much area has been damaged because of earthquake. The only way to get information from the satellite data. You can always get at least a reliable picture, accurate picture of that devastated area, and you can at least find, go for a map to give the idea to the district administrator or planners that where the relief has to go, how much rehabilitation is required, what are the ways you can reach to the place. Those information you can get only from the satellite survey. There are various kinds of, we call that disaster management cycle. There are various methods for this particular, various steps for it. Preparedness, we call disaster event, that means when disaster is happening. Then there is after disaster is over, then you have to talk about the disaster relief particularly. Then there are rehabilitation, reconstruction, and prevention. If you see, the satellite data has a role to play with all the four major stages of the disaster management cycle. We call the disaster management cycle. In case of preparedness, satellite data has a role to play with the detection, the monitoring, and the forecasting. So satellite data used to detect the disasters. You can monitor the disasters in a real-time domain, and also you can forecast. Nowadays, even we are quite capable of forecasting cyclone and things, even tsunami also we can forecast. Monitor the event during the time of occurrence, when disaster is happening, particularly the like chronic disasters like erosion or sometimes the coastal flooding or storm surge. You can find out how disaster is happening with the time, like how much area is getting inundated, how much the water is spreading towards the land, then when the water is receding towards the ocean, then how it is receding. All this you can also monitor in the satellite data. Now damage assessment is very important because it is directly related with your relief operation. How much area has been damaged, how much infrastructure has been damaged, how much agricultural land has been damaged. That will tell you how much relief you are supposed to put in that region. That is very important from the district administrator or the commissioner. They're supposed to know that the areas where maximum damages occurred, the areas which are maroon till, so they will put the food from the helicopter. Actually, the relief is supposed to reach at a position where you need to get the relief. Sometimes the relief comes and they will distribute in area where there is no relief is required. Relief is not going to those places where actually the relief is required. So those information you can get from the satellite data. Once you assess the damage, the total area of total amount of damage has happened and the areas which are maximum damage has been happened. Then also satellite data has been used for the hazard zonation. Hazard zonation is very important for the once damage is over, like there is earthquake. Bhuj earthquake in Gulf of in Kutch areas earlier. Those zonation or landslide zonation, they are very important for the rehabilitation purpose. Once houses are destroyed, once people have been destroyed, then you have to rehabilitate them. Why to rehabilitate them particularly? You have to rehabilitate them. You have to see that you should not build any houses in the flatland region. You should not build any houses where there is some active fault is going on, joints are there. So that way you can make some hazard zonation. According to the hazard zonation, you should go or build where there is no hazard chances are there or the least hazard areas. You have to rehabilitate them. Then reconstruction, mitigation and the prevention also satellite data has a huge role to play with. This is nothing to do with the coastal disaster. This is what talking about the so all kind of disaster putting together. What is the role of satellite data? This is what I was telling you, the disaster management cycle. You can see there is a mitigation, preparation, then when event is happening, then you have immediate response and you have to go for the recovery. So these management cycle you can see all are intertwined with each other. So everything has some relationship from the P impact, then during the emergency time, then restoration, reconstruction and particularly capacity building is very, very important, particularly for the disaster mitigation. Now we come directly to the coastal disasters. First, most important thing, let us see that what are the various kinds of coastal parameters which you can retrieve from the satellite data, both active and the passive. I am talking only from the spaceborne satellite data. In this table, you can see that in the first column, I have put various kinds of parameters. In the second is the present and the future satellite and the sensors. And third is the what are the country agency those satellites belong to. Like coastal landforms, landforms, wetland habitat, shoreline changes, marine pulse leaks, geological structure. Those you can very well map with the various kinds of optical data like AOV, sweeps, list 1, list 2, list 3, PAN, Costal Hazard, resource 1, 2, Landsat TM, ETM, and in OLA, then Spot PLA, MLA, Iconos, QuickBird, all kinds of satellite data will help you to map the land use, landform, coastal, wetland, habitat, those things. You can get the shoreline changes, geological structures, those things you can do. You can also map quantitative way the suspended sediments using MOS in IRSP P3 earlier, SEWS data, then also OceanSat 1, Ocean Color Monitor, OceanSat 2, Ocean Color Monitor, they will help you to map the suspended sediment in the water. And you can see the country like earlier, the waves list belongs to India, the Spot belongs to France, TM, ETM belongs to USA, and the Iconos belongs to USA. The OCM is basically our sensor and SEWS is the USA. Also you can do map the coastal bathymetry, you can map the surface current, also sea surface temperature is very much important for the potential fishing zone. Yesterday my colleague was taking class on oceanography, he must have briefed about the potential fishing zone. So sea surface temperature is very, very important for the potential fishing zone measurement, which you can get from the NOAA data from USA and also our MSMR from the P4. Also you can map wave height, wave direction, wavelength. They basically, these information you can get from the active sensor like Canadian RadarSat or European Space Agency's SAR, or also wave height you can get from the altimeter, like we in OceanSat 2 we have our own solar altimeter data, our own sensor, also surface wind you can get from the scattorometer, and MSMR also quick scat data in scatterometer in the quick scat, and also in the next OceanSat 3 there is a plan to put the sensor for getting the surface wind. Same way, basically we are talking about the wind vector. Also, you can talk about the wind direction from those kinds of active sensor data. Then sea surface topography we can get from the ISA altimeter, the Topex Poseidon data. You can do information for the sea surface topography, the geoidal surface. Then also again another important for the ocean biological productivity, particularly the chlorophyll, which is again important for the potential fishing zone concentration, that you can get from the sea waves or ocean color monitor in OceanSat 1 and OceanSat 2. This is the important parameter which we know from the satellite remote sensing data. Why? What is basically coastal zone where our all interest is today? It is, you can see, it is a transitional area between land and the sea. It is a band rather than a line. It's not a line. Line we talk about mainly the shoal line or the line where the land and water boundary line. But when coastal zone is telling you, I am talking about a transitional area. There is a part of the ocean and part of the land in the coastal area, and also it varies from the place to place. The width of this band varies from place to place and is determined by the interaction of the marine and the terrestrial processes. This zone is occupying around 15% of the surface of the globe, but within this 50% of the surface of the globe, around 60% of the world population are living. That means the population pressure on this coastal zone is tremendously high. 40% of the 1 million kilometer long coastline around the world is accessible and temperate enough to be habitable. It is not that everywhere you can go or everywhere you can stay. 60% of the human population are living in the coastal zone. 2/3 of the world major cities are lying in the coastal area. In India also, like in 4 out of these 4 metros, 3 metros except Delhi, they are lying in the coastal area. Others also, a lot of important cities like Vizag and other cities are also in the coastal area. Bhubaneswar, capital of the Odisha. It comes around 8% of the ocean surface comes under the coastal zone, because part of the land and part of the ocean is in the coastal area. 14% of the global ocean productivity happens here. 90% of the world fish catch. This is very important because coastal water is very productive, and that is why the chances of getting fish are more in the coastal water. 90% of the fish catch are coming in within this coastal water. 75 to 90% of the global sink of suspended river load are happening in the coastal water, because in the coast lots of rivers are bringing lot of sediments, nutrients, and they dump in the coastal area because they are the places where estuary forms. The estuary maybe also sometimes depending on the situation, the deltas may form. So also they bring lot of sediments. Those sediments are getting transported along the coastline. So 75 to 90% of the global sink of suspended river load are happening in the coastal area. Coast is of vital importance to the humanity. It is an essential fragile element of the global ecosystem. It is a zone of rapid transition, gradient and variation. It is very dynamic, very difficult to put boundaries around because it is a dynamic region. There is a high tide, there is a low tide, there is salt water intrusion in the coastal aquifer. So how much coastal water will go inside the land? Always it is debatable, because in the meteorology they say that the sea bridges goes up to what extent towards the land is the coastal area. So it's difficult to put sectors and boundaries. It's a highly dynamic region, and definitely it's a subject to multiple uses. Various kinds of activities are happening in the coastal area, so number of use is very high. If you see the population growth, particularly the disasters, or when we cover the hazard or disasters, basically we are much more concerned about the human life. And in India, in the coastal area, the population density is also very high, because India is basically the second largest populous country in the world. We see the increase in the population of a country up to 2011 census. So now we are around 121 crore people in our country, and a lot of people are living in the coastal area. So when there is a disaster like tsunami, cyclone, or storm surge, those things are happening, chances of casualties are very high. And it is very difficult to re-elevate the people within a short notice, particularly like during the time of cyclone or tsunamis, to re-elevate the people, or particularly evacuate the people from the place of the cyclone. It's very difficult. And because of the population pressure, so things become very complicated, and district magistrate and the administrator, commissioner, they also face a lot of difficulties, because so much of population are living in the coastal area. all the three metros, coastal metros, Calcutta, Mumbai, and Chennai, if you see the population density in the year 1951, 81, 91, you can see how the population has been increased in all the three metros in the coastal region. And if you see, this basically is telling you about the density of the population in the latest census. All the states basically, there if you see the coastal state like Tamil Nadu, Kerala, West Bengal, Odisha, there also density of the population is quite high compared to the northeast state of the Himalayan state. So coastal states are very vulnerable in that way when population density is concerned. And various kinds of coastal disaster management, there is a role on the space technology. Like if I talk about the cyclone, you have a role, as I told you, in all the disaster management cycle, satellite data has a role, space technology has a role to play with in the preparedness, relief, and the mitigation and the prevention scale. In case of cyclone, like you can, in the preparedness cycle, you can go for the detection, monitoring, and the communicating. Relief, definitely you can map the extent of the damage because of the cyclone. How much water has been inundated, how much area has been damaged, how much trees has been uprooted, all can be mapped very nicely from satellite data. So, extent of the damage can be mapped. Mitigation and the prevention, you can talk about the early warning system and their implementation. This is very important when mitigation and the prevention is concerned. The same way in case of coastal flooding, earthquake, the landslide, sometimes the volcanic eruption in the coastal area, coastline erosion, point and the non-point pollution, sea level rise, mangrove and the coral reef decline, the algal bloom. See, in the all kind of disasters happening in the coastal area, you can see, I'm not reading everything because all the PDF files has already been circulated to you. In all these kinds of coastal disasters, in all the management cycle, satellite data has a role to play with. Basically, if we try to divide the coastal hazard, we can divide it in two ways. One is there's the short-term disasters and one is the long-term disasters. Particularly, short-term, I'm talking about mainly those hazards which are coming very fast, also goes very fast. But in case of long-term disasters, they are chronic disasters. Short-term disasters means cyclone, hurricane, typhoon, tsunami. Long-term land subsidence, sea level rise, coastal erosion, they are the long-term disasters. Coastal hazard, as I told you, they are the mainly short term and the long term, and there is cyclone, storm surge, or storm tide. They are the disasters which are happening. Like in case of cyclone or hurricanes, I'm sorry for the slides, they are automatically going one step ahead. They are the tropical revolving, they are called cyclone, they occur in the Indian Ocean region. And in case of they are tropical and they are the all low pressure system of the depressions, the cyclone and the hurricane, and depending on which area they are happening, the name cyclones and the cyclones they have been given, but they are basically low pressure area depression. Because of the low pressure, all the air from the surrounding area, they are coming and trying to occupy those space, and basically cyclone is formed. And when there is a tropical cyclone, you can see that the impact is manifold. There will be strong wind associated with the tropical cyclone. There will be local sea level rise or storm surge, and there will be heavy rain associated with the cyclone. The strong wind and the heavy rain and the sea level rise, they cause the flooding. They will cause the flooding in the local area. And damage to the structures, like damage to the buildings, damage to the sometimes trees, the electric line, and all other things, they may cause the loss of life. Also, flooding causes loss of life. Heavy rain, which is flooding, and this flooding is causing the destruction of the crops. And also strong wind, which is associated with the cyclone because of the low pressure region, they also cause the destruction of crops. So one tropical cyclone, basically, it's causing damage to the structure, flooding, loss of life, destruction of crops. So many things are happening with one tropical cyclone. Now, if we see the number of frequencies, particularly the months in the cyclone in the Bay of Bengal and the Arabian Sea, it has been seen the Bay of Bengal is very prone to the cyclone compared to the Arabian Sea. There are reasons for it. because cyclone conditions are much more favorable in the Bay of Bengal than the Arabian Sea when the sea surface temperatures and other things are concerned. And also a lot of cyclone I, they are getting generated in the Pacific Ocean, they are migrating in the Bay of Bengal, though they are not basically originated in the Bay of Bengal, they are from the Pacific Ocean, which is the major source of the world cyclone. So they are coming and they are finally getting into the Bay of Bengal. Their chances are not there in case of Arabian Sea. And if you see the month-wise distribution, the month like September, October, November, they are the months where frequency of the cyclones are very high. Then compared to the December, January, February, they are the comparatively calm period. So if you go for the cruise or other things, they are the better month to go on board. This image is showing how the cyclone I is moving with the INSET series of satellite on the Orissa super cyclone happened in the year 1999. So here you will see how the eye is moving from the Bay of Bengal and how it is reaching the coastal Orissa, and finally how it is revolving along the Orissa coast without going through Western Bangladesh initially how it was predicted. And because of this, the devastation was huge, and it has been termed as a super cyclone. So during 28th October to 30th October, these 3 days, the eye of the cyclone remained in the coastal Odisha only. So you can from this image, but the INSET series, you can find the movement of the cyclone track of the eye, and also the landfall. Actual what time the landfall has been happened, and then consequence also you can find out from the further analysis. This is also one of the inside 1D image showing the landfall. This is the just eye is touching the you see the land and water boundary. So landfall image on 29th October 1999 near Paradip. The landfall was near Paradip, so maximum devastation happened in those regions. As per the source of the Orissa government, there was a huge devastation, but though it is a government source, maybe the real scenario is much more higher than this. So there is around 10,000 people lost their life, around 15,000 villages affected. You can see around 130 lakhs, so more than a crore people affected. So much of crop area affected, houses affected, fishing net, fishing boat, around 10,000 fishing boat we lost. So these are the huge loss to the entire nation because of this super cyclone. But scenario is much better. Now the prediction is very high. Recent cyclone like cyclone Hudud, you have seen how the prediction worked very nicely, and hardly except some I think 3 or 4 people died. That too from some other reason. But we didn't lose any single human life because of the cyclone Hudud. Though definitely there will be some loss in the infrastructure and other things, but most places the human life we could have saved because of the very fine prediction. This is the one way to predict the effect of the cyclone on the coastal vegetation. You can see these are the NDVI image, which is basically called normalized difference vegetation index, is IR minus R by IR plus R, having the values -1 to +1. -1 representing basically the very poor state of vegetation condition. Towards the positive side, the vegetation condition is healthier vegetation. So here you can see this is the image. This is the pre-cyclone NDVI, 11th October. This is the post-cyclone NDVI. You can see particularly this color. This is the all NDVI values. The map you can see the legend. There are the values, particularly 5, 6. This range of values. This is all coastal vegetation. This red, this color. This is the mangrove, Vitrakonika mangrove. This is the Vitrakonika mangrove. So these are the all mangrove patch, quite healthy vegetation. You can very well you can see, and you can find out the total area of the mangrove in this region. But after the super cyclone, you can see lots of this region. This is all green patch. They have been converted to the NDVI values 2. This 2 is 0.2 basically multiplied by 10 to get a whole number, and you can see even this entire mangrove patch. This color vegetation value, which was 6, that has been reduced to 5. This entire range, the green color has been replaced by the red one. You can see the blue one, the wall water has gone inside particularly. Here also there are small, hardly few mangrove patches remaining. So this will tell you the effect of the vegetation, the coastal vegetation. Any kind of this effect you can find out from a satellite data pre-cyclone and the post-cyclone. You can find out the NDVI. You can talk about how the health of the vegetation has been affected. But fortunately, as soon as the water recedes, here basically the post-cyclone image, maybe lots of vegetation, lots of mangroves, small trees there under the water. But after when the water started receding, the mangroves will again come up with due time, unless until they are uprooted. And so those type of scenario also you can see. But for this you need to have a good temporal resolution set. But high resolution, high spatial resolution at the same time high temporal resolution satellite data is not available. So in this case we are using the IRSP4 OCM, this is 360 meter resolution NDVI image for the pre and the post cyclone, showing the status of vegetation around Mahanadi Delta. Here you see in the pre cyclone, they are all mangrove patch. This bar representing this red color or the yellowish color is the healthier vegetation, and this blackish one is the poor state of the vegetation. You can see this map, so many pixels are having red and the yellow color. That means vegetation condition is good. But after the post cyclone, you can see there are hardly any pixels having red or the yellow color. So almost they are all green or blackish color. So the almost entire area, the condition of the vegetation has become very poor. But you can see that when this image, this was 11th October, this is the 14th November. Then when I am going Goa acquiring image, same area, December 14th, January 13th. Then you can see again the mangrove patches are coming up. All the red pixels have come up. They are not there. You see the image here. In 14 November 1999, those pixels are having the red color. They are not there. But when the water recedes, this started coming up again. Okay. Then again, you see the number of pixels, the red color, they are becoming higher and higher. Or some yellow color pixels has come up. Some more reds have come up. So it's regenerating of the vegetation in this region. So vegetation is really coming up. So you can, in this way, you can temporarily monitor how the area has been reacted to the particularly the disasters and how the area is responding to that calamity. Okay. This is also the multi-temporal satellite data in Gulf of Kutch, showing the status of the coastal vegetation, mainly mangroves, how it is changing with the time, how you can find out the salt incrustation in this region and how they are causing damage to the mangrove patches. So this is the data from 1998, 1999, 2000 up to 2001, different period time data to tell you the red patches are the mangrove patches and how they are going to degrade with time. That can be shown very nicely from this image. Also, you can do a lot of study from the oil spill. This is basically initially the oil spill was trying to, we try to understand oil spill from the IRSP4 OCM FCC in a region in the Gulf of Kutch, where you can see this elliptical area in November 13, 1999 image. There was no spill, no black color line like this has been seen here. But 15th November again we got the image because it's OCM, it is every alternate day you can get the image. There is something peculiar has seen over here. Then people thought that maybe this is maybe because of the oil spill. But precisely to know whether this is oil spill or not, basically you're supposed to go to the field and check it, verify it. But another way you can find out that if you go and get a thermal image of this region, particularly the oil spill is showing a very cooler signature than the surrounding. So, but fortunately we get a image of the NOAA SST, we derive the SST from the NOAA of that region, and we find that in the same region, the same patch here, we get a very cooler signature. So it may be a because of this patch, because of the oil slick, but definitely again I am telling you that this is not a conformity test. After this, definitely you are supposed to visit the field and find out whether really some spill is there or not. But it will give you only some idea. Yes, there may be some oil spill, because oil spill study nowadays people are more conversant with using the active sensor data, which give you really conformity test about the oil spill. Like this, you can see this is the radar set image. So these are the oil spill patches. You can find out. You can even see the sips, the white color patches. They are the sips, and then from some sips because dumping of the oil. These are the oil spill. You can find out very nicely from the radar set image. Mainly the active sensor image, they can pinpoint the oil slick much better than the passive sensor. Here again the oil spill detection in the from the radar set image. This is very clearly you can see because this is a high resolution multispectral 2.8 bit resolution satellite data from the digital globe. It has been downloaded. You can see the ship has been anchored, and these are all the oil spill from the ship. The used well, it has been dumped near the ship. You can find out the migration of the oil spill. Nowadays, various kinds of models are available in the NOAA rescue and the response project and other sites where you can find out that how the migration will happen with time, like in which direction the oil will move, and when it will hit the coast, how much the coastal resources it is going to be affected particularly. The migration will again depend on the prevailing wind condition, the tidal condition, the current condition. If you incorporate all those conditions in the model, you will be able to find out that how the oil spill track is going to follow, and when they are going to hit the coast, and after hitting the coast, the area, how much resources are there and how much resources are going to be affected. For this, how much money you are going to be, how much money will be affected in like US dollar and other things. That also there are publications in various international journals. People have worked up to that level, so that is also possible. And few models I have seen you can also download freely from the net and use this model for the oil spill, particularly for the track prediction. That means how the spill will migrate with time with input parameters like, as I told, wind, current, those kinds of parameters, tide. If you put those parameters, you'll be able to find out. This is again from satellite data. This is pollution dispersal seen on the IRS 1D history of Trivandrum coast, 24th February 1999. You see, this is a Trivandrum airport. Very nicely you can see. This is the conduit, and from here they put the pollution, how the pollutant plumes is migrating from along the coastal area. Very well you can see from a simple satellite image without any enhancement and anything. From satellite data you can find out, yes, there is some pollution is happening in the coastal area. Satellite data is very much important, particularly multi-temporal satellite data, to find out the shoreline changes. Some case study has been done in lots of areas in India by various organizations, our students and other departments. See, this is in Dharma estuary, part of the Maharashtra Delta and Odisha coast. This is basically the shoreline we digitized from the survey of India toposits, which has been surveyed in the year 1972. And IRS 1D history data acquired on March 19, 2001. So there is a gap of around 30 years. So how the area has been changing? The yellow one is a survey of India toposit digitized land and water boundary, which has been put, and the backdrop you can see the satellite data. So you can find out using this this area the erosion has been happened, because the yellow line was in the water earlier in 1972. Now the land water boundary has gone far inside. That means this much of area has been gone under the water. So erosion has happened in this region. The same thing, same area like here the Paradip port. Earlier the configuration of the speed was like this. Now in the satellite data speed is like this. So there is a changes in the speed. New barrier island has come up. This island was not seen in the survey of toposit in 1959. In the satellite data in 2001, you can see this island. So new barrier island has come. The entire earlier this part, this is the extended part of the beach. This is no more here right now. So this part is entirely governed with water. So this entire area has been eroded very severely. But at the same time, one side of the port, Paradip port, is getting eroded, but the other side you can see accretion has been happened. Here particularly you can see the new beach has come up. The land water boundary earlier, the yellow one was here, but now it is here. That means this much of a land we have acquired. Particularly whenever you are going to establish any port in any region, this type of erosion and accretion in the various sides of the port, you will be able to see, because it basically disturbs the longshore drift, and this is basically cause for the erosion and the deposition in the region. This is another study which has been carried out on a small island in Bay of Bengal area called Sagardeep Island, Sagar Island. This island we have surveyed for several times, and we have tried to understand how the island is behaving with the time, like which part of the island is eroding, which part of the island is accreting, and it has been seen that it is not that in different time domain that all the parts of the island is eroding. it has been seen that some part of the island is eroding in some time frame, and the same part is also getting accreted in the other time frame. So it has been seen that in the 96 to 99, the erosion trend is dominating. Then again 98 to 99, the accretion trend is dominating. Then 99 to 2000, again accretion trend, and 96 to 2002. Overall, if you see, the erosion trend is dominating, and it has been seen that erosion trend is likely to be continued in the near future. So this change in the erosion and accretion is also changing in the time, depending on the various kinds of oceanographic conditions. So it is not easy to say that erosion is happening. That means it is going to be eroded for the another couple of years. That may not be true also. And in this region, we are trying to find out the erosion hotspot, particularly from the multi-temporal satellite data and other the field-derived information. And it has been seen that wherever there are the mangrove patches, like there is a creek we call the Chemaguri, there are lots of mangroves are there, and these mangroves are basically acting as a shelters area. So these areas the erosion is less. So these areas accretion is mainly dominating. But the other parts, particularly the sandy beaches areas where there is no mangrove and other coastal vegetation, those areas are the mainly the erosion prone region. So that way you can find out which is the erosion hotspot in any coastal region where erosion is happening more than the accretion or the vice versa. Some more study has been carried out in the Bay of Bengal in the Mandarbani region. Some study has been carried out and we have extracted. I'm not going in detail we have extracted the soil line in the various time domain on the landside ETM plus and the list 3. Various kinds of techniques are there to for extraction the soil line, like water index, band ratio, the density slicing, NDVI, isolated classification, IHS transformation. So these type of techniques are available, which can you can use them in the soil line, and overlaying the different soil line in the different time domain, you can find out how the soil line is changing with the time. So you can see that in multi-temporal domain in the different time from 1950 to 2005, how the area, which part is eroding and which part is depositing. There are techniques to find out the changes in the soil line, like there are softwares called DDAS, Digital Soil Line Reference, by USGS. So there you can make some cross sections, various kinds of, and find out how soil line changes is happening in the time. And it has been seen that in a particular soil line, it is not that the entire soil line is eroding. Some part of the soil line is getting eroded, some part of the soil line is getting accreted. That way you can divide the soil line in the different cell. Like you can see here, the cell 1 is a highly erosion prone. Cell 2 is cell 1 is a very highly, cell 2 is the highly, cell 3 is this part is the moderately, and this part is the cell 4 is the mainly the least erosion dominated region. That means in the entire stretch of the coastal area, the erosion rate is different. Different area is behaving differently with time. So we can find out particularly the erosional regimes in this region. So this part is overall. This part is we can say they are the erosional regime with varying erosional potential in a different area depending on the coastal configuration and other things. And this part particularly where there is a inlet is there. This part is mainly the depositional regime or the accretional regime. That way the coastal area is defined. Basically, causes of the deposition and the erosion in the coastal area, as you know, is mainly tides, waves, rip currents, longshore currents, sea level rise, cyclonic storms, and various kinds of anthropogenic activity. They are mainly responsible for the erosion and depositional activities. Now, this is all about the coastal erosion and deposition. I will just touch upon few on the tsunami waves. As you know, that tsunami basically happened because of the subsurface earthquake, or maybe the subsurface earthquake or subsurface volcanoes. It is a Japanese word, came from the harbor waves. At the source, tsunami waves are very fast. They travel around 500 to 800 km per hour. When they are coming near the source region, near the coast, their wavelength will be diminished, their wave height will be increased, and also their speed will be diminished. But that too speed will be around 70 to 80 km per hour near the coast. But their energy will remain constant. That is why they will be most devastated, and even 70-80 km speed of the waves which are dashing along the coast. So if you are there at the coastal area, you cannot even run by 70 to 80 kilometers per hour. These are the some image downloaded from the internet showing the pre and the post tsunami image of the Banda region in Indonesia. This is the pre-tsunami. You can see all the agriculture area, all the urban region very nicely seen. But after the tsunami, everything has been devastated. This is the mainly the badly affected countries because of the tsunami. Here was the tsunami source. This is a Sunda Trench. This is a basically subduction zone. And this is the area, particularly the red color, you can see Sri Lanka, the Indonesia, the Thailand, Andaman Nicobar, this part of the Indian coast, the eastern side, like Machilipattanam, Nagapattanam, Chennai, Karaikal, so these areas are Pondicherry, these areas have been highly affected. As I was telling you, this is the velocity at the source is around 1000 km per hour. You can see the wavelength is very high, around 800 km. Particularly, the wavelength is so high with a very small wave height. So even the sea, which is there in the offshore, he will not able to understand that there is some tsunami has happened below him. But when these waves are coming, traveling a long distance near the coastal area, they are, you can see their velocity diminishes. But in order to conserve the energy, the amplitude increases. That means wave height is increased. So this is the equation from where you can find out that how with the decreasing the velocity, the wave height or the wave amplitude is increasing. But this is mainly because of the near the coastal area, the bathymetry decreases and waves started filling the bottom. Because of this, mainly the wave become more compressed and the waves height increases, but wavelength become smaller and smaller. And velocity definitely it will be reduced quite a lot, but the energy will remain constant. So that is why it is written. It is not felt abroad the sea or the seen from the air in the open. You will not able to understand. There is just, but it can be measured by the buoy or the satellite altimeter because there will be difference in the wave height, particularly because there will be upward perturbation of the water column. You can find it out for the students, particularly if there is a Sumatra 2004 earthquake, how much time it will take from this point to reach the Sri Lankan coast, because if you know this horizontal distance and you know the speed of the waves, you will be able to calculate how much time it will take to the Sri Lankan coast. Particularly this calculation is not coming in this PPT mode, but it is there in the PDF which has been given to you. First you try to do it of your own. Same way, how much time it will take to go to the Thailand, that also you will be able to find it out. This is our area in the Marina Beach, pre-tsunami and the post-tsunami image. You can see the pre-tsunami this part, particularly this area you can see new channel has been created after the post-event. You can see the white beaches of the Marina. This is all water has come on the top of this, on the top of the beaches. You can see this vegetation this has been destructed. This region. Satellite motion sensing data is very much helpful for finding out the inundation due to tsunami. Penetration of water body because of the tsunami towards the land can be easily traced from remote sensing data. So that is how much water has gone. Inundation limit you can find it out. The inundation line derived from the ground survey can be superimposed over the taluks or the village map using GIS to have an idea about the affected agricultural area, population, human population, and the infrastructure. Because nowadays maps are available, like taluk level map showing the all agriculture area, even the different taluks, different population. If you know all these things very precisely, then particularly you from the field work of the satellite data you find out the inundation line, superimposing it on the top of this map on the GIS, then definitely you are able to find out how much population has been affected, how much agriculture area has been affected, how much infrastructure has been affected. That is very much possible to do it. I will show you some of the images acquired during those days by National Remote Sensing Agency, that time National Remote Sensing Agency. This is a Andaman Nicobar Trinket Island. This is a pre-tsunami image IRSP6 AOHIPS 21st December. You know 26 December 2004 the tsunami came. You can see this is the day when tsunami came. This is the image. This is the 4th January 2005. You see here there is a solid island, but after this this island has been broken into two. So there is a channel has been developed water from this side to this side. Now see, even there are a lot of clouds because there are lots of rains are happening in those times. But after this, you can see this. Again, it has started. Some kind of connection is happening, but it is a very thin way, not like this. Even this part, you can see the water has reached over here, but here again, there is a lot of water. Nothing. You see, almost again, this top part has been broken into two. So from this type of satellite data, you can find out how the things happened during tsunami. And this type of final maps have been generated. This is a map generated by those days. IGMPD comes under the ocean development. This map is showing you you see the blue line here, H1. This is the total inundation area, and within this, it has been superimposed on top of the taluk level boundary, high tide line, low tide line, everything has been shown over there. And then you can find out this what are the number of what are the moza or taluks. How much, what are the name of the villages, what is the population of agriculture area, how much has been inundated, how much area has been affected, all those things can we find out. But at the same time, you can see that it's not a straight line. The inundation extent is also varying from place to place. Some area where there is a canal, inundation has gone far inside the land. So the extent of the inundation of seawater depends on few factors like earthquake parameter, particularly how strong is the earthquake. Definitely stronger the earthquake, the tsunami will be the more stronger, and most likely the more inundation will happen. So bathymetry is very important parameter for tsunami particular prediction. Then beach profile, how the nearshore beach profile is there, like whether there is a mangrove pair, whether there is a sand dunes, and what is the digital elevation near the beach. Then land topography, the velocity of the tsunami waves and the frequency. Due to these parametric variations, because these variations are there in a coastal area in different place to place. So because of this parametric variation, the inundation limit is also varied from one location to the other location, as you can see from here. Some field work we did just after the tsunami in the Nagapattinam region, that how much area has been inundated. You can see the different like different stations. You can see there are all various kinds of stations, 1, 2, 3, 4 like this. So what is the inundation limit? How much water has gone? How is the penetration inside the water? Some are even 1 kilometer, some are 500 meters, 700 meters. You can find out that how much water has gone. And these are run-of-height with in this region, in the Nagapattinam region. What is the run-of-height during the tsunami? So this type of map can be generated to give you the feeling that what is the run-up, what is the inundation limit, and this is the configuration of the coastline of this region. As we know, during the tsunami, suddenly the water, there was certain withdrawal of the water in this region. You can see the unprecedented withdrawal of the sea between the pulses of tsunami waves at the Tiruchirundur and near the Kanyakumari coast, particularly. So there was no water, almost divided in water. Water has gone much inside the sea. But suddenly, because of this unprecedented effect, people will come to see what has happened. But this is the warning. Suddenly the water will come with huge speed, so hardly people will get time to run away from the coast, and there will be total devastation. You can see all the various kinds of illuminate places which are far in the ocean, so they have been dumped in the coastal area near in the Kanyakumari coast because of the tsunami. So this all illuminate has been deposited, so they have been thrown from the offshore region, the nearshore coastal region in the tsunami, in the Kanyakumari coast. You can see withdrawal of the sea of the Sumatra region with the tsunami. In the Sumatra, there is a total withdrawal of the sea. The entire region which is supposed to be under the sea, there is no water now. But this is the warning that now what is going to come. This is how the model has been developed just after the tsunami in 2004 in the different time frame. If you see after it start, you see different minutes. So you can find out how much time it has taken to reach the Sri Lanka or the India. So 10, 20, 30 minutes it is coming. Just now it has hit. That's around 120 minutes. That means after the tsunami generated, almost after 2 hours, it has hit the coast. So as soon as you can predict the tsunami from the various kinds of tsunami models, or the bottom pressure recorders, or tide gauges, or the seismograph installed around the world ocean, and data immediately you can get from United States Geological Survey or the agencies. Then you can run the model and you can find out that how much time you are getting before the tsunami waves is reaching the coast. Not only this, if you have the various kinds of other information about the nearshore region, you can find out that what will be the wave height while breaking at the coast and how much water is penetrating towards the land. So accordingly this you can plan, like you can find out that where you evacuate the people, what are the higher altitude area where the even during inundation the water will not able to reach. Those things you can do very well, but you will not get much time, maybe some 2 hours or something you will get, and that within this time also you have to do all those things during tsunami. But model is quite good. Even they tell that NQuest is basically the nodal agency in Hyderabad for this, and our model is better than model which is there doing for so many years in the Pacific Ocean. This is the region in the Gulf of Khambat, showing you the salt affected mud flat. What I am showing you particularly, you can see these patches, they are the salt pans. In this region, the Gujarat is the highest salt producing state in our country. They are the all salt, because salt production is basically, we call it is a low investment, high yielding business. That means you invest less, but yield is quite good. Here basically your main raw materials is free. See, they are the all creeks. You can see various kinds of creeks. They are the Bhavnagar city, Bhavnagar. So along the creeks during hybrid time water is, and you can take the water and spread it over the field, and get it evaporated. So almost you will get the raw salt and mix with some chemicals and little bit processing, your salt is ready for it. But unfortunately, in this region, in India, we have the semi-dominant tide. That means there are 2 high tide and 2 low tide in a single day. So in morning 6 o'clock is the one high tide, in evening 6 o'clock you will get the next high tide. But within this time, if you miss the first in the morning, like if you cannot take the water in the creek during high time, you have to wait till evening 6 o'clock. But basically we don't have so much of time to wait. What people do over there, they pump the groundwater, which is also salty, saline region, and that pump groundwater and try to produce water out of this. But without knowing the scientific consequences, like more pumping groundwater, you are getting negative hydrological gradient, so more salt water is going inside the land. That is what is happening in this region, and it has been seen that because of this, around 15-20 kilometers per inside the land, the saltwater intrusion has gone inside, and lots of villages, lots of population, they are eating the saltwater, having the chlorinity content more than 1000 mg per liter, which is against the quality of the water, drinking water quality of the water given by the World Health Organization and the European Union, and it has a long impact for the health of the human being. So here you can see, it has been seen that different contours showing the different chlorinity content has been drawn, because we collected water sample in from the various sources like tube well, the talabs and other places, and it has been analyzed in local university from the chlorinity content. You can see all those villages like Goga, Kalakala, Alang. So they are all the villages, they are drinking, they are covering under 1000, the violet line, 1000 mg per liter with that drinking water, chlorinity content. The safe region is the green, this is less than 250 mg per liter, which is the safe index, chlorinity index. But this is around few places, around 10 km, 15 km from the land, and this is mainly happening because of the pumping of the groundwater for the production of the salt, which is totally unscientific, as we all know, the geology, particularly the equation of the Guyvan and the Hodgman. We try to model the scenario from the groundwater vulnerability analysis. We collected a lot of boron data in this region and tried to see the characteristics of the aquifer in this region. And few parameters have been considered, like which have a direct role for the saltwater intrusion. The most important mappable factors like groundwater occurrence, what kind of aquifer, unconfined leaky aquifer hydraulic conductivity, which is most important parameter for the conductivity of the saline water inside the aquifer, depth of groundwater level above the sea, distance from the shore, the distance inland particularly from the shoreline, impact of existing status of the saltwater intrusion in the area, thickness of the aquifer which is being mapped. So taking these all parameters together and their values in different time domain like pre-monsoon season, post-monsoon season, because in the post monsoon there will be a lot of showers and scenario will change. And there is a numerical ranking system, which is we call the Galvin model. You can see the GALDIT, it has come from here, and different scores has been given, and then finally so these are the area. These are the all well locations in the Bhavnagar district. All the data has been collected. Like data like total depth, 3D, static water level, total diesel solid, carbonate, bicarbonate, chloride. This data has been collected from the Gujarat Water Resources Development Corporation for the year 1983 to 2000 in every 5-year interval for the pre-monsoon May time and the post-monsoon in the October period, because we have to generate the scenario in the pre-monsoon and the post-monsoon time. So these are the all scenario in the pre-monsoon, post-monsoon when the groundwater vulnerability is concerned around the Bhavnagar city. You see the red area is a highly vulnerable area, and they are the Galvin score. 90 highly vulnerable, 70 to 90 vulnerable, 50 to 70 is the moderately vulnerable, less than 50 is the non-vulnerable region. So in the pre-monsoon you can see this entire region is highly vulnerable. Then this is coming the vulnerable region. This is the moderately vulnerable. This is not vulnerable. But after post-monsoon, and there are a lot of showers, lot of fresh water goes inside the aquifer, you can see the highly vulnerable region has been restricted to here only. So all these highly vulnerable, particularly the Bhavnagar area, this is coming under the moderately vulnerable zone. And also you can see the non-vulnerable area has also been increased. Also the moderate, less vulnerable area has also been increased. So this type of study needs data in various seasons, pre-monsoon and post-monsoon, and different time domain. Then only you will be able to get the idea how the scenario is changing with the time. In continuation with this, you can put in the GIS, you can see the colorimetric contour less than 3 per liter, and this is again more than 250. This is post monsoon, this is the pre monsoon, and all the villages, all the dotted line, they are the location of the villages. This has been put to show you the what villages which are coming under the like greater than 2000 mg per liter, 1000 to 2000, then 500 to 1000, 250 to 500. What are the villages? How many villages are coming within this in the post monsoon and the pre monsoon? Definitely scenario number of villages will be changing with time. And we know the population. Then you can find out how much population, how much total number of people they are covering under this greater than 250 mg per liter chlorinate content. Those kind of analysis you can do. So you can generate some pie chart, population affected due to salt water intrusion in May 2003. This was the total population within this range, this chlorinate content. And in October 2003 is the pre-monsoon, post-monsoon. You can find it out. So now the last slide, the summary. We can conclude that space technology plays a role in almost all the components of the disaster management cycle that we have already told. Coastline mapping and change direction are essential for safe navigation, resource management, and environmental protection and sustainable coastal development and planning. With the advancement of technology, more dependency of the coastal monitoring is observed on remote sensing tools and products. That is very, very important. Without remote sensing, it is very difficult to address all the issues in the coastal zone. In order to maintain the overall balance of the coastal morphology as well as the environment care and the awareness is needed for every level, starting from the grassroots to the government level. Satellite data is also useful for monitoring disaster response activities, damage assessment, reconstruction, and the rehabilitation. Thanks. Thank you very much.